Good afternoon, everybody. My name is Gaurav Chaudhary. I am Assistant Professor in IT Department at Eigen Engineering College, Ghaziabad. The topic of today's lecture is multivariate analysis. Now, there are three techniques for classical multivariate analysis. One is PCA, which stands for Principal Component Analysis. Second is Correspondence Analysis, and third is Multidimensional Scaling. These techniques are used for analyzing samples that are in form of observation, which are vectors. So, PCA is a method of transforming the vector observations into a new set of vector observations, whereas in correspondence analysis, the relationships between the rows and columns of a table of counts can be highlighted using the correspondence analysis. In multidimensional scaling, which is a technique for constructing the set of vectors from the set of dissimilarities. Now, coming to PCA in detail. So, PCA, what we do is we try to reduce the dimension of features per observation. So, we have to follow some fixed number of steps to find the reduced features, which are optimal also. So, the first step is we have to standardize the data set. So, suppose we have got a data set which has got 4 features, and as we have 5 training examples, features being from F1 to F4. So, first we need to standardize the data set, and for that we need to calculate the mean and standard deviation for each feature. So, once we calculate the mean and standard deviation for each feature, we tabulate the mean and standard deviation for each and every feature. After we find the mean and standard deviation, we apply that for every feature and for every row in the data set. So, the data gets transformed by using the formula for x nu is equal to x minus mu upon sigma. So, here we are actually reducing the dimensions. We are able to do so because the eigenvectors of the covariance matrix are actually the directions of axis where the most variance or maximum information is available, and hence it is called as principal components, and they preserve the maximal amount of information. And the eigenvalues which are associated with the eigenvectors, they give the amount of variance in each principal component. So, if we are able to rank our eigenvectors in order of their eigenvalues from highest to lowest, we will get the principal components of higher significance, and they will be uncorrelated. So, this is the transform matrix after standardizing the data set, and then after standardizing data set, we calculate the covariance matrix for the whole data set for population as well as for sample. So, the covariance matrix for the given data set will be transformed and will be calculated as below, which is this matrix. So, here we can see that in the diagonal, the covariance reduces to the variance of the feature for the diagonal values of the matrix. Since we have standardized the data set, so the mean for each feature is 0 and the standard deviation is 1. So, in similar way, calculate the other covariances, and which will result in the below covariance matrix. This is the final covariance matrix. After we have calculated the covariance matrix, then we will proceed on to calculate the eigenvalues and eigenvectors. An eigenvector is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. The corresponding eigenvalue is the factor by which the eigenvector is. We calculate the eigenvalues and eigenvectors. So, the eigenvector is a non-zero vector that changes at most by a scalar factor when that linear transformation is applied to it. The corresponding eigenvalue is the factor by which the eigenvector is scaled. Let A be a matrix, in our case the covariance matrix, V be a vector and lambda be the scalar that satisfies the equation AV is equal to lambda V. Then lambda is called the eigenvalue associated with eigenvector V of A. So since we have already know that V is a non-zero vector, the only way this equation can be equal to 0 if the determinant of A minus lambda is equal to 0. So the matrix should be invertible and the determinant of A minus lambda I should be equal to 0. Solving the equation, we get the lambda values which are the for each and every feature. So solving the equation for V vector with different lambda values, we get the values of the vector, the 4 vectors for the 4 corresponding features. Going by the same approach, we can calculate the eigenvectors for the other eigenvalues and we can form a matrix using the eigenvectors. So here we can see that we have got the, for each and every feature, we have got the eigenvectors and the corresponding eigenvalues. After getting so, what we have to do is we have to sort the eigenvalues and their corresponding eigenvectors. Since the eigenvalues are already sorted in this case, so no need to sort them again. And we have to pick the k eigenvalues, so we will pick the first 2 eigenvalues and form a matrix of eigenvectors. So if we choose the top 2 eigenvectors, the matrix will look like this, comprising of 2 columns E1 and E2. So once we have got the top 2 eigenvectors, we can transform the original matrix by using the formula which is feature matrix into top k eigenvectors equal to transform data. So this is how we are able to transform our initial matrix into the transform matrix, which contains the maximal information with respect to the chosen top 2 vectors, eigenvectors. So the principal components are orthogonal to each other and the orthonormal basis implies that the basis vectors are orthogonal to each other and have a unit magnitude. The aim is to use the feature vector formed using the eigenvectors of the covariance matrix to reorient the data from the original axis to the ones represented by the principal components, hence the name principal components analysis. So this is just a code snippet using the sklearn library to calculate the PCA, principal component, and do the principal component analysis for the given matrix in our example. Now coming to the second technique, which is correspondence analysis. So correspondence analysis is a way to represent the structure of the incidence matrix of the given matrix, and the incidence matrix are also called as two-way contingency tables. An example of a 5x4 incidence matrix with marginal totals is shown in figure in table 3.17. Here what we have to do is, our aim is that we have to produce a picture that shows which groups of staff have which smoking habits. So there is an implement assumption that is smoking category and staff group are related. So we have to find the association between the variables in the given matrix. So if we see the staff group members, which are senior managers, junior managers, senior employees, junior employees, secretaries, and the smoking category being none, light, medium, heavy, and their marginal totals are given. So in this, what we have to do is, we have to find the structure between the variables of the table. In other words, we have to find the association between the two variables. So there are two ways to find the association between the two variables. One way is using the log linear modeling method, which is the oldest method. But instead of using the log linear modeling method, what we will use is the chi-squared distant method, which is based on the traditional test for association between categorical variables, which is also called as the chi-squared test of association. This is the test that was used before log linear models were developed and is still used if either you do not have a computer handy or you do not want to introduce your students to log linear modeling. Now coming to the third technique, which is multidimensional scaling. So multidimensional scaling is the process of converting a set of pairwise dissimilarities for a set of points into set of coordinates for the points. So we have to convert a set of dissimilarities which is given, which has some description. That description has to be converted into a set of coordinates for the points. The problem here is that the location of the points in space or the configuration of the points is unknown. So the aim is to find a configuration in which the pairwise distances between points approximate the dissimilarities as closely as possible. So it may be difficult first hand to see how the pairwise dissimilarities might be known if the configuration is not known. So example of a dissimilarity could be the price of an airline ticket between the pairs of cities. So this is the example. Now for the airline ticket example, the idea will be to construct a map in which the distances correspond to the cost of the travel between the cities. So if we take the distances which correspond to the cost of the travel between the cities, we will be able to find the configuration of the points. So that in multi-dimensional scaling, again we have got two types of approaches. One is the classical scaling and other is the ordinal scaling. So the classical scaling assumes that the dissimilarities are Euclidean distances, that is distances like those that we meet in everyday life with the same geometric properties, whereas the ordinal scaling assumes merely that the dissimilarities are in same order as the distances between the points in the configuration. So if the dissimilarity between 2 points say A and B is 0.5, then the dissimilarity between A and third point C is 1. Then this says that the distance between A and C in the configuration should be bigger than the distance from A to B, but not necessarily twice as big. So because it should follow the same order, the difference order it should follow. So if the difference between A and B is 0.5 and the dissimilarity between A and C is 1, then the distance between A and C in the configuration should be bigger than the distance between A to B. So the rank order has to be followed. So coming into details of classical scaling, it is also known as the metric scaling. And the name metric scaling is used because the dissimilarities are assumed to be distances or Euclidean distances. The name principal coordinate analysis is also used, and it is used because there is a link between this technique and principal component analysis. To derive a configuration, we have to start off by imagining that we know the configuration. So because we don't know the configuration, we have to reach to the configuration from the dissimilarities matrix. We have to reach to the configuration, but to start with, we initialize our configuration matrix by imagining it to be some values, and then working out what the pairwise distances would be, and then trying to reverse the process. So suppose let X be the matrix whose rows specify the positions of the M objects in the configuration. So this configuration would lead to a matrix of pairwise distances D, for which the matrix is given using the formula DKL is equal to X xk transpose xk plus xl transpose xl minus 2xk transpose xl. So in this matrix, your dkl is the distance between the objects k and l, and the elements of D are obtained from X using the following relationship. So what we have to do is we have to reach from D to X, and initially we are assuming some value of X, which is the configuration, and we have to reach to the final configuration using the dissimilarity matrix. Now coming to ordinal scaling. Now ordinal scaling is used for the same purposes as classical scaling, but the difference here is only that the dissimilarities are not metric, that is they are we would think of as distances. So they are not the Euclidean distances. So the in ordinal scaling is sometimes called non-metric scaling because dissimilarities are non-metric. So in ordinal scaling, we seek a configuration from the dissimilarities matrix, and in which the pairwise distances between the points have the same rank order as the corresponding dissimilarities. So if delta KL is the dissimilarity between points K and L, and dkl is the distance between the same points in the derived configuration, then we seek a configuration in which dkl is less than equal to dab. If the condition delta kl is less than equal to delta ab is satisfied. So again, from the assumed configuration, we are finding the dissimilarity matrix, and we are working back the improved configuration for our dissimilarity matrix. So this completes the topic of multidimensional scaling and also the topic of multivariate analysis. Thank you.